Hello, everyone. My name is Aryeh, and I'm a staff member at ALP. And today we'll be going over modular arithmetic, which is really helpful in AIME number theory problems because, we could be dealing with really large numbers that often show up on AIME that have still 1,000 is quite like a high number for an answer, but we don't want to work with necessarily large numbers. So modular arithmetic really helps us bring them down. So as a general definition, modular arithmetic deals with remainders from numbers and their operations. So for how it looks like, we say that 3 is congruent to 8 mod 5. And this is so because when 3 is divisible by 5, we have a remainder of 3 because 3. And then when 8 is divisible by 5, we have a remainder of 3, so they're the same. And note that throughout this lecture, we'll be using this notation A line B. What this means is that A is a divisor of B, so we can see 2 is a divisor of 4, 3 is a divisor of 6, and so forth. So going back to the 3 and the 8 that are congruent in mod 5, we can keep going. So 3 is congruent to 8, which is congruent to 13. And see, we're just adding 5 to each of these, and this keeps on going for however, and say 1,003. They're all equal, all congruent to 3 mod 5. And note we can actually go the other way as well. So to get from 8 to 3, we subtract 5. So subtracting 5 from 3, we get -2 is congruent to 3 mod 5, sorry. And that's congruent to -7 mod 5, so forth. Note that we can actually, a lot of different, all the operations can be used in modular arithmetic, such as addition. So let's look at the two numbers 14 and 98. And we want to find there's some 98 minus 14, 98 plus 14, 98 minus 14, 98 times 14, and 98 divided by 14 in mod 13. So instead of doing all of these things first and then getting them down to mod 13, so let's start with 14. We can just simplify earlier on. So 14 plus 98. So 14 is congruent to 1 mod 13 because 14 minus 13 is 1. So this is just 1 mod 13. And 98, 7 times 13 is 91. And 98 minus 91 is 7. So 98 is 7 mod 13. So going back to our addition problem, 14 plus 98 is the same as 1 plus 7, which is equal to 8 mod 13. And hopefully it's clear now how modular arithmetic can help us with some much larger numbers. Moving on to 98 minus 14. You can apply the same thinking here. 98 is 7 mod 13, and 14 is 1 mod 13 to get that they're 98 minus 14 is 6 mod 13. Let me scroll down a little bit. Oh, here. And then we have 98 times 14. Here it's real, 98 times 14 is quite a big number. And then having to divide by 13 to find a remainder, we can just, still 98 is 7 mod 13, and 14 is 1 mod 13. So we can just replace those with their respective mod remainders to get that their product is equal to 7 mod 13. And then last we have 98 divided by 14. Same exact thing. We just do 7 is congruent to 7 divided by 1, which is congruent to 7 mod 13. So next, note that this also works because exponents are technically multiplication as well. So we can actually use modular arithmetic to find exponents in the last digit of a number. So for example, take the number the large number 3 to the power 20,000, 2022. And we want to find the last digit. And whenever something asks for like the last digit or the last so many digits, we always want to work in mod a power of 10. So this is just last digit. So since this last digit, it's just the one digit, so that's like, so we want to work in mod 10. So 3 to the power 1 is congruent to 3 mod 10. And then 3 squared is 9, which is 9 mod 10. And then we have that multiplying the 9 by 3, we get 27. But 27, so 3 cubed, sorry, this is 3 squared. It goes on. 3 cubed is 27, which is the same as 7 mod 10. And now we just have to do this, multiply the 7 by 3 to get our to get 3 to the 4th is congruent to 21 is congruent to 1 mod 10. And when we multiply 3 to the 4th by 3, we're going to get a number that's 3 mod 10. So it restarts this like little cycle. So now when we're asked to find 3 to the power 2022, we just need to find the remainder when 2022 is divided by 4. So 2020 is divisible by 4, so it's just 2022 is congruent to 2 mod 4. And then we just want the second one. And so this is like 1, 2, 3, and this is technically a remainder of 0. So since it's 2 mod 4, the last digit is just 9. And yes, modular arithmetic really helps a lot with finding patterns. Now that we have some like introductory material out of the way, let's look at 4 past AIME problems and try to use modular arithmetic to solve them. So we begin with 2014 AIME 1 problem 8, which states the positive integers n and n squared both end in the same sequence of 4 digits a, b, c, d when written in base 10, where digit a is not 0. And we have to find the 3-digit number ABC. So we start by using what we know. We have that the last 4 digits of n and n squared are the same when written in base 10. So the last 4 digits we used for last digit 10 to the power 1. So we're gonna use mod 10 to the power 4, which is equal to 10,000. But we're just gonna leave it as 10 to the power 4. So this problem gives us that n squared is congruent to n mod 10 to the power 4. Let me just redo that 4. Okay, there. So then to simplify this, we're going to subtract n from both sides, which you can do in modular arithmetic, as we've seen. So n squared minus n is congruent to 0, which means that n squared minus n is divisible by mod 10 to the power is divisible by 10 to the power 4. Then factoring to the left-hand side gives us n times n minus 1. This is still under the same mod 10 to the power 4. N minus 1 is congruent to 0. Mod 10 to the power 4. So what this means is that we have n times n minus 1 is a multiple of 10 to the power 4. And note that n and n minus 1 are relatively prime. So this gives us 2 cases. The first case, and 10 to the power 4 equals just 5 to the power 4 times 2 to the power 4. The first case is if n is a multiple of 5 to the power 4, and n minus 1 is a multiple of oops, I'm just gonna clear that up. Sorry about that. I'll just right there. Now that sorry about that. Let's go back to that. So going back to our problem, we see that in this first case, so five to the 4 is 5 to the 4 is the divisor of n, and 2 to the 4 must then be the divisor of n minus 1. So in this case, we're going to just, like, the first power of 5 to the power of 4 is 625, which means n minus 1 would be 624. And note that 624 is actually divisible by 2 to the power 4, or 16. So that means in this case, our answer would be n equals 0.625, which does work. However, the problem statement says that a cannot be the first digit of the last 4 cannot be 0. So this case does not work. Moving on to our second case. This is just basically the two things are flip-flopped. So this means n is divisible by 2 to the power 4, or 16, and n minus 1 is divisible by 5 to the power 4. Looking at the first power of, and n minus 1 has to be less than n. So 5 to the power 4 is 625. And the greatest power of 16 greater than that, since 624 is divisible by 16, is 640. However, note that 640 minus 625 is 15, which is not, they're not 1 apart. So we have to find two numbers such that they're 1 apart. Notice that 16 is congruent to 124, which is actually congruent to -1 mod 125. This will help us find a number such that case 2 works. So for each, like, as we get, here we have 625, which is 5 to the power 4 times 1. That means that in here we found that the smallest multiple of 16 is 15 greater than that power of 5 to the 4. What this here is saying is that so, like, if we go to the next power of 625, which is 625 from 2 is 1250. The next multiple of 16 is going to be 15 minus 1 is 14 higher. So 1264. But still, here's still 14 difference between the two. So we need to find our number of n minus 1 is going to be just 625 times 15. So that we get a difference of 1. 625. Which equals 9,375, which is n minus 1. And note that here, the 9 is non-zero, so this actually works. Well, this is n minus 1, which means n is 9,376. Therefore, our answer is just these three numbers, which is 937. Moving on to our next problem. We have problem 14 from 2019 AIME. So in this problem, we have to find, it's a short problem statement, which is quite common about these. It's a short problem statement for such like a high level placement problem. So it seems like it can be easily found the answer to, but it's actually quite difficult. But modular arithmetic definitely helps make that a bit easier. So we have to find the least odd prime factor of 2019 to the power 8 plus 1. So let's just write this out in modular, like our form that we've been using for modular arithmetic. We have that 2019 to the power 8 plus 1 is congruent to 0 mod p. And we need to find p because then this just means the 0 means that it's p. 2019 to the power 8 plus 1 is divisible by p. Then let's subtract both sides by 1. sorry. Is congruent to -1 mod p. Then, as I said, like exponents, we can do that in modular arithmetic. So we're gonna, in this problem, we're just going to square both sides, which is quite a helpful tool. 2019 to the power 16, 8 times 2. The -1 squared is 1. So this 2019 to the power 16 is 1 mod p. Next, so note that the 1 on the right hand side is quite important, because we can write this as any k such that 2019 to 16k is congruent to 1 mod p. Because we're just multiplying 1 by itself k times, k additional times, which will always equal 1. And then we're going to use Fermat's little theorem, which states that for any prime p, a to the power p minus 1 is congruent 1 mod p. And I would recommend watching the ALP video on this theorem. So this shows us that 16 is a divisor of p minus 1, which means that p is in the form 16a plus 1. So it's 1 greater than a multiple of 16. So now all we have to do, since now we basically have a nice number to work with, we just want to start testing out small cases. So that are prime, because there are not a lot of p's greater than 16 that are 1 greater than 16 that are prime necessarily. So p equals 17 is our smallest number, and this is prime. So we're going to work with this to see if this is possibly an answer. So you want to find, right, 2019, we're working in mod 17 now. 2019 to the power 8 is congruent to 13 to the power 8 mod 17. And this is just by finding how many 17s we can take out of 2019, basically. And then squaring 13, we get that this is congruent to 169 mod 4, which is in turn, since 170 is divisible by 17, this is congruent to -1 to the power 4, which is congruent to 1 times 1 equals 1 mod 17. So this does not work because we want to find a prime such that right here, that to 19 to the power 8 is congruent to -1 mod p, but for 17 2019 today is congruent to 1 mod p. So let's just keep going with p such that they are 1 greater than a multiple of 16. So then adding 16 to 17, we get 33. However, 33 is not prime. Adding another 16 is 49. 49 is not prime. Keeping on going. 65 is below 5, not prime. Again, adding 16 gets us 81, which is not prime. Takes the perfect square. And then adding again gets us 97, which is prime. So maybe this will work. Let's see. Now we need to find again. 2019 to the power 8. 2019 to the power 8 is congruent to -18 mod 8. Sorry, -18 to the power 8, just by looking at the closest multiple of 97 2019. And then this is congruent, squaring -18, we get 324 to the power 8. Again, we are in mod 97 because p is 97 in this case, which is congruent to so just looking at the 324, this is congruent to, sorry, this should be a 4. 33 to the power 4, which is congruent. 33 squared is 1089 to the power 4. And we just keep on going. So 1089 to the power, sorry, 1089 squared. Let me just erase that so it's clear. Yeah, 1089 squared, which is in turn congruent to 22 squared mod 97, showing that we get 484. And since 485 is a multiple of 97, we have that this is -1 mod 97. Therefore, 97 works. So 97 is our smallest prime factor of 2019 to the power 8 plus 1. All right. We have 2 more problems to work on. Our next problem is from 2020 AIME, and this is AIME 2, and this is problem 10. So here we need to find the sum of all positive integers, and so it's that when 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed is divided by n plus 5, the remainder is 17. So like this addition right here is not really like nice to work with. So the first thing we have to think of is trying to get this into a nice multiplication and division expression, because those are much nicer to work with in modular arithmetic when we're working with large numbers. So let's just like, it's like 1/3, 1 to the power, 1 cubed is equal to 1. And so 1 cubed plus 2 cubed, oh, sorry, let me just get rid of that, change. 2 cubed is equal to 9. That's interesting because 1 is a perfect square, is 9 is a perfect square. So let's keep this going. So add 1 cubed plus 2 cubed plus 3 cubed is the same as 9 plus 27 is 36. Wow, another cube. And thinking ahead, 4 cubed is 64, and 36 plus 64 is 100. So this is an interesting pattern we see here, and we have to try to like find a formula for this. So, so we have, this is 1 squared, this is 3 squared, this is 6 squared, this is 10 squared, and this is 4, like up to 4 and equals 4. I have to think, how can we get there? Well, notice all of these, well, it's mainly just a bunch of like guess and check, like just trying to find a pattern that works. And through and then you'll figure out that the sum of the first n cubes is just n squared times n plus 1 squared all over 4. And this can be proved with induction, which we're not going to be covering in this video, but yeah. So this is quite important because now we want to, this is equal to this original expression here. And we want to find this mod n plus 5, and we want to find an n such that when this here is divided by n plus 5, the remainder is 17. So another thing, so now we're going to try to like kind of manipulate this expression right here. Sorry, with the squared. But so we're gonna like let's let q be the quotient when this expression in circle in red, I'm just gonna get the 2 in there, is divided by n plus 5, and then we have our remainder, which has to be 17. So what we're looking for an n is that. Then we're gonna put all the n's onto one side so that we have q equals an expression in terms of n. So doing this, we get q equals n squared times n plus 1 squared minus 68. I'm just gonna fix these here. All over 4 times n minus 5. And notice that q has to be an integer. This is important because that means 4 times n plus 5 has to be divisible. But 4 times n plus 5, it has to be the divisor of n squared times n plus 1 squared minus 68. So looking at this equation, we're looking at the number 4. Let's just get like a blue right here. Notice that we can actually take this 4 out of this entire thing, because 68 is divisible by 4, so that's all good. And notice that n squared times n plus 1 squared is going to be divisible by 4 at all times. And this is because if n is even, then n squared will be divisible by 4. However, if n is odd, then n plus 1 squared is going to be divisible by 4. So you can kind of just take the 4 out of this equation for now. So we're just going to rewrite this as q equals n squared times n plus 1 squared minus 68 all over n plus 5. And notice that this might give us an extraneous root or 2 when solving for this. Next, we're just gonna like multiply everything out in the numerator so that we get one polynomial. Doing this gives us a numerator of n to the 4th plus 2 times n to the cube, 2n cubed plus n squared minus 68 all over n plus 5. Then we're going to use synthetic division, which is a good dividing technique when dividing polynomials. And don't worry, like if you don't know synthetic division, you can use long division as well, but it's just a faster method to find the remainder when the numerator is divisible. So we just put -5 here. So we have 1, 2, 1, 0 for the n term and -68. And we want the remainder, and we're looking for the remainder. So just filling this out, we have -1, -5 is -3, 15 gives us a sum of 16, -80, 0 plus -80 is -80, and -80 times 5 is 400, and 400 minus 68 is 322. So what we now need is 300, sorry, this is not 322, it's 332. I'm gonna erase that and rewrite that just so it looks better. 332. Now the only way in which we won't have a remainder here, so that q, like the original q here, what it can be an integer, is that n plus 5 needs to be a divisor of 332. So we have that 332 has to be congruent to 0 mod n plus 5. So now we just find divisors of 332, and doing that yields that 332 has divisors 1, 2, 4. Sorry, it's a bit slow. 83, 166, and 332. And we have to be careful with these roots because not all of these are, and this is for and this is mod n plus 5, so we're gonna have to reduce down. Note that 1, 2, and 4, these can't be we can't use these in our final tally for for values of n, because since this is mod n plus 5, we need all these numbers minus 5 is negative, and we're just looking for positive integers n, so these are all canceled out. Then as I said earlier, we might have extraneous root because we got rid of the 4 earlier in this problem. So looking at 332, we actually see that when multiplying our original expression that we found right here, circle in red, for the sum of the first n cubes, it is not a remainder of 17 when divided by 332, sorry. So we can also get rid of this. This leaves us with these two solutions, 83 and 166 for n plus 5. So just since then n can be 78 or 161, which 78 plus 161 is equal to 239, which is our final answer. Heading on to our last problem for this video. We have problem 12 from the 2016 AIME 1. And this problem is asking us to find the least positive integer m, which is that m squared minus m plus 11 is a product of at least 4 not necessarily distinct primes. So we're going to start with like smaller primes. So note that m squared minus m, we're going to use a lot of different like mods in this problem. M squared minus m plus 11 is never even. This is true because if m is even, then m squared minus m will be an even minus an even, which is an even number, and then plus 11 will be odd. So one of the distinct primes can never be even, so never can be 2. And then if m is odd, then m squared minus m is going to be an odd minus an odd number, which is going to be an even number, and an even number plus 11 is always going to be odd. So one of the 4 primes is never even, so that means it's never 2. Never 2. Next, we have that. So let's let p be one of the primes that divides m squared minus m plus 11. Note that p will also divide 4m squared minus 4m plus 11, and this is only so because we're just multiplying the m squared minus m plus 11 times 4, so p will still be a divisor of that. And the reason we did this is because we can then turn this into 2m minus 1 squared plus 43. And manipulating expressions and equations is a great idea when you're working with modular arithmetic. So now we need to find a p such that, and this is p, this is all congruent to 0 mod p. Like write that. This is all congruent to 0 mod p, meaning that p divides p. This is divisible by p. Sorry. So now let's go back to like here, this part of the equation. Subtracting 43 from both sides, we have that 2m minus 1 squared is congruent to negative 43 mod p. So looking at this, I think the best idea to start, because some of these primes have to be like small, or else m is going to be too large to be like a 3-digit or 2-digit number. So let's like work with p equals 3. See if there's an m such that p equals 3. So note that here, 2m minus 1 squared. Well, let's just go to the negative 43. Negative 43 is congruent to, because we're adding 42 to that, negative 1p mod p. And note that the left-hand side is something squared. And nothing in modular arithmetic can, since like you can't multiply 2 real numbers to get negative 1, except for in mod 2, but since we have here, we can also test all values of like mod 3, but sorry, this should say 3. There's never going to be a square of something mod 3 that gets us to negative 1. So mod 3, so p equals 3 can't work. P equals 5, we didn't get negative 43 is congruent to negative 3, which is not negative 1, so we keep adding another 5. 2 is congruent to 2 mod 5. Here I'll show you like how we test out all the cases. So note that all integers are either 0, 1, 2, 3, or 4 mod 5. And we're not even going to deal with like the 2m minus 1 squared, because we're just dealing something squared. With 2 minus 1 is always going to be an integer, so it's going to be one of these 5 things. So 0 squared is congruent to 0, which is congruent to 0 mod 5. 1 squared is congruent to 1, which is congruent to 1 mod 5, and so forth. So 2 squared is congruent to 4, which is congruent to 4 mod 5. Then the next we have 3 squared, which is congruent to 9, and subtracting 5 gives us 4 mod 5. And finally, we have 4 squared is congruent to 16, which is congruent to 1 mod 5. And note here that none, we have 0, 1, 4, and 4 and 1 when all these numbers are squared. None of these are equal to the 2 that we need here. So therefore, mod 5, p can't equal 5. Let's try one more prime, the next prime, which is prime p equals 7. P equals 7. Here again, we note that, sorry, let me just scroll down so you can see. It's negative 43 mod 7, adding 42 to that, which is 6 times 7, is congruent to negative 1 mod 7. And using the same logic for p equals 3, or we can just use the same reasoning that we used for p equals 5, we'll find that there is no integers that squared is negative 1 or 6 mod 7. So mod 7 for p can't work. All right. So, and then the next, let's just actually keep going because that might not be an item, because we should probably find a prime sometime soon. So let's work with mod p equals 11. Negative 43 is congruent to adding 4 to both, to negative 43 gives us 1 mod 11, which is quite good because 1 mod 11 times 1 mod 11 gets us 1 mod 11. So we have 1 or negative 1 mod 11 squared gets us to 1 mod 11. So 11 can work, and that can be part of our like 4 primes. So this means, since we're trying to find like the smallest value of going back m, we have that m, well, we're gonna, yeah, m squared minus m plus 11, was it? It was m, right? Yes, m squared minus m plus 11 has to be greater than or equal to 11 to the power 4. And this is because none of the primes less than 11 could work. Therefore, we have the m squared has to be greater than 11 squared, which equals 121. For this equation to be greater than 11 to the power 4. And previously we found that here, either -1 or -1 mod 11 can work for like this equation. But sorry, we need to check. We're actually looking for values of m. So m doesn't have to we need m to be this has to be the left-hand side of this inequality that's circled in blue has to be a multiple of 11. Therefore, m has to be either 0 or 1 mod 11. And this is because 0 and 1 mod 11 are the only two like remainders when divisible by 11, such that m squared minus m is congruent to 0 mod 11. Which makes it that our expression circled in blue is divisible by 11. So trying the smallest integer greater than 121, that's 0 or 1 mod 11. Well, 121 is 0 mod 11. So we just have 122 is our next. 122 has a remainder of 1 divisible by 11. So we have m equals 122. And here's when we just use a little bit of multiplication. So we want to find 122 squared minus 122, plus 11. And this is 122 squared minus 122 is just 121 times 122 plus 11. And we're just going to factor the 11 out of this. So there's just 11 times 11 times 122. Sorry, that's a multiplication. 10 plus 1. And 11 times 122 plus 1 is equal to 1343. And just testing divisors because it has to be less than, the smallest divisor is not that large. We're just testing divisors. we see that 1343 is 17 times 79. So M equals 122 yields us a number that's 11 times 17 times 79. The good thing is that we have 3 primes. However, there's only 3. And going back to what the problem wants, we want to find the least M, such that the product of at least 4. So let's just keep trying to see if we can find. So the next one, next number that's 0 or 1 mod 11 would be 121 plus 11, which is 132. Oops, sorry, I'll change that. M equals 132. Here we have this yields 132 squared plus 132. Sorry, minus 132. Minus 132 plus 11. And then factoring the 11 out of the first 2 terms. Well, yeah, we're just making them one multiplication. We have, this is 121. Sorry. Well, this is 11 times 12. Sorry. Yeah. So this is 132 squared. So it's just 132 times 132 minus 1 plus 11. And factoring this, we have, this is 11 times 12, because 132 divided by 11 is 12, times 131, which is 132 minus 1. Sorry, that shouldn't end there. Plus 1, because 11 divided by 1 is 11 divided by 11 is 1. And then we got just 131 times 12 is just 262 plus 1,310, which gives us 1572. And adding the 1 gives us 1573. It's just 11 times 1573. And notice that the sum of the alternating digits are the same. It's like 1 plus 7 is 8 and 5 plus 3 equals 8. So it means 1573 is divisible by 11. And then we find that this is equal to 11 times 11 times 143. And then note that 143 is 11 times 13. So we have that this is just 11 times 11 times 11 times 13, which is great because these are 4 not necessarily distinct primes, which means that M equals 132 is our final answer. So that's it for today's video. I hope you learned something. We went over quite a good amount of problems, learned some new things. If you have any questions, feel free to ask on our Discord server, and make sure to watch our other videos on YouTube posted to practice for the upcoming AIME. And that's it for now. Thank you for listening.